Hi and Assalamualaikum. In this video, we will do a presentation of our Calculus 1 subject assignment, which is explained in the topic differentiation, maximum and minimum problems. Before that, let me introduce my group members. Hi, my name is Nur Azwa Airin binti Hamdan and my matric number is 2020829832.
Hi, Assalamualaikum everyone. My name is Nur Tasnim Tihani binti Muhammad Zuki. My matric number is 2020887894.
Hello, my name is Nur Shafika binti Osman. My matrix number is 2020890666.
Hi guys, sorry for your time, but I know you can solve my problem, right?
Yes, of course. After all, it can help us to understand this topic better.
So guys, don't waste our time. Let's discuss question 1 until 3. Let's get started.
Alright, but before that, let me tell you guys the overview of what this topic is about. Okay, first, concept and definition of differentiation. You should know that differentiation is one of the most important concepts in calculus. It is a process of finding a function that outputs the rate change of one variable with respect to another variable. From that, we know that differentiation is an action of computing a derivative. The derivative of a function y equal to fx of a variable x is a measure of the rate at which the value y of the function change with respect to the change of the variable x. It is called derivative of fx with respect to x. Also, derivatives are a fundamental tool of calculus. Next, we move to the concept and definition of maximum and minimum problems. Okay, many application problems in calculus involve function for which you want to find maximum or minimum values. The restriction state or implied for such function will determine the domain from which you must work. The function, together with its domain, will suggest which technique is appropriate to use in determining a maximum or minimum value. For example, the extreme value theorem, the first derivative test, or the second derivative test. The process of finding maximum or minimum values is called optimization. Finding the maximum and minimum values of a function also has practical significance because we can use this method to solve optimization problems such as maximizing profit, minimizing the amount of material used in manufacturing an aluminium can, or finding the maximum height a rocket can reach. Now, let's look at the objective of maximum and minimum problems. By the end of the presentation, we are able to use partial derivatives to find critical points for a two-variable function. To ensure that we understand well in applying a second derivative test to identify a critical point as a local maximum or local minimum for our two-variable functions. To ensure that, we can look at critical points and boundary points to determine absolute maximum and minimum values for a two-variable function. Next, I will pass the presentation to Azwa.
Definition of maximum and minimum problems. When it is said that fx has an absolute or global maximum at x equal to c, in the case of fx less than and equal to fc for every x in the domain we are dealing with. When it is said that fx has a relative or local maximum at x equal to c in the case of fx less than and equal to fc for every x in some open interval around x equal to c. When it is said that fx has an absolute or global minimum at x equal to c if fx more than and equal to fc for every x in the domain we are working on. When it is said that fx has a relative or local minimum at x equal to c if fx more than and equal to fc for every x in some open interval around x equal to c. Strategies for solving maximum and minimum problems. First, we need to read the problem carefully. If relevant, draw a picture. Second, label the picture with appropriate variables and constants, noting what varies and what stays fixed. Third, translate the problem to an equation involving a quantity to be maximized. Represent the quantity in terms of the variable of step 2. Fourth, try to express your quantity as a function of one variable. Lastly, use the derivative to determine the maximum or minimum values and the points at which they occur.
Continue with problem statement 1. A rectangular plot of land is to be fenced using two kinds of fencing. Two opposite sides will use heavy-duty fencing at the cost of 6 ringgit per meter, while the remaining two sides will use standard fencing at the cost 4 ringgit per meter. If the total cost of fencing a rectangular plot is 1,200 ringgit, find the dimension of the rectangular plot of greatest area. The solution is, the first step, we need to draw a rectangular plot of land and label it. I use x as the length and y as width. The second step, find formula for the quantity to be maximized. The question said, two opposite sides will use heavy-duty fencing at the cost of 6 ringgit per meter, while the remaining two sides will use standard fencing at the cost 4 ringgit per meter, and the total cost of fencing the rectangular plot is 1,200 ringgit. So, I translate it into an equation which is 2 times 4x plus 2 times 6y equal to 1,200. Then solve the equation to get a formula for the quantity to be maximized. I solve the equation and get x equal to negative 3 over 2y plus 150. The third step is, we should identify the quantity to be maximized as a function of one variable. For this question, I use area of rectangular as the quantity to be maximized. The formula is a equal to xy. We substitute x from step 2 into the formula. Then we get a equal to negative 3 over 2y squared plus 150y. The fourth step is, find the value of y when dA per dy is equal to 0. dA per dy is negative 3y plus 150. Equal it with 0, then solve it to get the value of y. Y is equal to 50. The next step is, find the second derivative and substitute y from step 4 to difference between maximized and minimized value. The second derivative is negative 3, which shows that the quantity is maximum value. The last step is determine the value of x. Use the equation from step 2 and substitute the value of y into the equation. X is equal to 75. The dimension of the rectangular plot of greatest area for this problem is 75 meter times 50 meter. Now we move to the second problem.
So, this is problem statement for question 2. MAS Airlines requires that rectangular baggage carried on an airplane be such that the sum of dimension, length, width, and height is 135 cm. Find the dimension of baggage that will maximize the volume given that the length of the baggage must be twice the width. This is the steps to solve the question 2. First, draw an illustration of package, which is a rectangular box, and let variable x be the width, 2x the length, and y the height of the box. Step 2. The sum of dimension of the package is given to be 2x plus y equal to 135, so that y equal to 135 minus 3x. Step 3. We wish to maximize the total volume of the package, so it will be v equal to 2x power of 2 times y. However, before we differentiate the right hand side, we will write it as a function x only. Substitute for y, getting v equal to 270 x power of 2 minus 6 x power of 3. Step 4. Now differentiate this equation, getting dv over dx equal to 540x minus 18x power of 2, and let dv over dx equal to 0, and we will get x equal to 30. Step 5. Substitute for x to get the height of the package y, and we will get y equal to 45 for the height. So now we get all the answer for the dimension of the package that will maximize the volume of the package, which is length equal to 60 cm, width equal to 30 cm, and height equal to 45 cm. Lastly, step 6. Differentiate the equation from step 4 and substitute x from the equation to show that the dimension of the package that will maximize the volume, and we will get the maximum volume is negative 540.
Next, we move to the question 3. Closed box has a volume of 15,000 cm3. The length of the box is 3 times of its width. Find the dimension of the box that will minimize the surface area of the box. Hence, find the minimum surface area. Step 1. You have to find volume of closed box using formula L times W times H equals to V. So I declare L as 3x, W as x, H as H, and we will insert in the formula, and you will get 3x times H equals to 15,000, 3x squared times H equal to 15,000, and we put H in front, so you will get H equals to 15,000 over 3x squared. Second part, I use the formula surface area of closed box. So you will get 2 times 3x times H plus 2 times 3x times H plus 2 times x times H equals to s. Cx squared plus cxh plus 2xh equals to x, and we replace h equals to 15,000 over 3x squared into the formula surface area of closed box. Cx squared plus cx times 15,000 over 3x squared plus 2x times 15,000 over 3x squared equals s. And after you summarize that, you will get cx squared plus 14,000 over s equals to s. Step 2. Find the dimension of the closed box using derivative. After you differentiate that, you will get 12s minus 14,000 over s squared. To find the critical point, we declare as ds over ds equals to 0. So 12s minus 14,000 over s squared equals to 0. So you will get s equals to 14.94 cm. To determine whether the critical point is maximum or minimum, you have to find second derivative. So you will get 18,000 over s cubed plus 12, and you will get 36. It will be minimum. So next you can find h equal to 15,000 over 3x squared. So you will get h equals to 22.40 cm. So the answer is length of the box is 44.82 cm, width of the box is 14.94 cm, height of the box is 22.40 cm. Step 3. Find the minimum surface area. less s equals to 14.94 cm. So cs squared plus 14,000 over s equals to s. When you replace s, you will get 4016.16 cm squared. After studying this topic, you should be able to understand the idea of differentiation and find a suitable formula or method that fits the question given. Integration is not only a mathematical term, but it is given a way to solve a problem in real life. With such ability to describe the real world, being able to solve differential equations is an important skill for mathematicians. We can conclude that minimum and maximum problems can solve using second derivative method. The question of practical applications of integration in daily life. Integral calculus or integration is basically joining the small pieces together to find out the total. That's all from me.
Thank you guys for helping me today. Now I get to know more about solving maximum and minimum problems.
No problem. I gotta go now. See you guys soon. Bye.
Bye. Have a nice day, everyone.